Alright, AP Stat students, welcome to our video lecture. I hope, or I don't hope, I know that you're all so excited to be watching this video. There's nothing else you'd rather be doing, and nowhere else you'd rather be than right here learning about everybody's favorite subject, statistics. So I appreciate the enthusiasm, and the same things apply in this video lecture as they would in class. You know, make sure you're wearing your uniform while you're watching this video. That's a given. Make sure that if you're wearing a jacket or a sweater, make sure, of course, it's Father Ryan outerwear. And no chewing gum, no cell phones. You guys know the drill. I don't have to tell you these things. But if you have a question during any point during the lecture, just raise your hand. And I of course will not be able to answer it, but you can keep your hand raised, and as you're walking into class on Monday, and I see that your hand is still raised, I will assume that you have a question, and I'll of course answer it then. So that will be good. So let's get to it. Section 1.3, describing quantitative data with numbers, highlighted in our favorite color, purple, Father Ryan purple. So what we're going to get into in this section is some math. Actually, we've primarily been dealing with emphasizing that this is a writing course, but here we're going to tie in the math and some numerical calculations that we can make to help complement our descriptive things that we've gone over so far. So quick review over what we have gone over so far. Section 1.1 was analyzing categorical data, and that was distinguishing between categorical variables and quantitative variables, and going over the representations of categorical variables, which are graphically pie charts, bar graphs, and we delved into the probability tables a little bit, the marginal conditional distribution. I know that those can tend to be a little confusing, and if that's the case, that's not abnormal in any way, but we will get more in depth into those in chapter 6. So just hold tight. I hope that you'll have a better understanding of those when we get to those in chapter 6 and probability. So section 1.2, of course, was the displaying quantitative data with graphs. So that was the dot plots, the stem and leaf plots, and the histograms. So everybody's favorite acronym, SOX. Shape, center, spread, and outliers. Shape, center, spread, I emphasize a little bit more just because those are going to be a given anytime we talk about a distribution. Outliers, they'll depend on whether they are present or not. So, but we've talked about these all, and now we're going to talk about some numerical representations of this acronym, shape, center, and spread. More so, center and spread. And a way to actually calculate whether we can classify a observation as an outlier or not. So that will of course be useful as well. So let's get to it. This page right here, you can pause it if you'd like, but all that was just what we're going to be going over in this section. So the mean is a measure of center, and this should be a review for all of you, I would hope, that we learned about the mean in elementary school, or grade school, and I'm sure that all of us have seen it before. But X bar is another way. You'll probably hear me refer to it as X bar from time to time. Average is probably the most common way of referring to the mean. You'll see that in our homework problems and in the book and on the exam, I think, as well. Probably will be referred to as average, but it all means the same thing. There's no difference, and there's no really better way of referring to it. It's just just know that it all means the same thing, and be familiar with each because they might refer to it as a certain thing. You want to be able to recognize it, of course. But finding the mean is very easy, right? You sum up each individual observation, and you divide that sum by the total number of observations, or the sample size, right? N is our sample size. So if we have, if I ask you to find the mean between the numbers 1 through 5, right? The mean of those numbers. So 1 plus 2 plus 3 plus 4 plus 5. That should be 15 divided by our total number of observations, which would have been 5. There were 5 numbers. So 15 divided by 5, our average would be 3. So pretty easy breezy right there. And that should be review. This notation or formula right here is something you'll see again on the AP exam. They'll give you a formula sheet for both the multiple choice and free response section of the exam, and it'll have this formula in there. This symbol right here is the Greek symbol sigma, and it is just the sum of each individual xi. The I stands for individual, as I poorly write it. I apologize. It's some of that 4th grade state handwriting championship handwriting right there. So uh, you guys can remember that always, that your AP Stats teacher was a state champion in handwriting. So something a lot of people uh, are not able to say, and honestly probably not many people would actually admit. But I'm proud of it. So the N, of course, is our total number of observations or sample size, as we will refer to it as in this course. And throughout this course, if I say what's N, I'm talking about sample size. Next slide, the median, that's another measure of center that we will use a lot, especially when dealing with skewed distributions, and I'll get into why that is here in a bit, if you don't know already. But the median is our midpoint of our data or our distribution. It is based on position, and it is the exact center of our distribution. This is a nice symmetric one, but our median would be there, right in the middle. And 50% of our data would be to the left, and 50% of our data would be to the right. Finding the median is very easy. You just arrange all observations from smallest to largest, and if the number of observations is odd, the median is very easy to find. Ooh, that's ugly. But if it's even, it's a little trickier. So I'm gonna show you why that is just real quick on the next slide. So let's do, if n is odd, real quickly, how you find what position. So median's based on position, right? So if we list all of our observations in chronological order, we're looking for a certain position, and whatever value that is located at that position is our median. So if we have 21, a sample of 21, how we find what position we're looking for is this formula right here, n plus 1 divided by 2. So for this one, if we do n plus 1 divided by 2, that's going to be 21 plus 1, so 22 over 2, which is very easy calculation. The 11th position, so we would count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and the 11th number ordered chronologically would be our median, so 11th observation. But when we get into even number samples, it's a little trickier, just in the sense that if we use this formula, n plus 1 divided by 2, and we have a sample size of 20, that's going to be 21 divided by 2, which comes out to 10.5. So the 10.5 position, or the 10.5 observation, we will not have a 10.5 observation. So we will actually have to look between the 10th and the 11th observation. And what we will do is we will calculate an average of those. So if the 10th and the 11th observation are the same value, that's very easy. It'll just be whatever that value is. But if they're different values, we'll calculate an average of those values. So what can happen is you'll have a median that's actually not even a value of our distribution, but that's okay. It's still a representation of center. The mean is not going to be a value most likely either of our observation, but um, it it gets a little tricky for this even sample size, and I think actually the example I have on the next slide is an even sample size, and it is n equals 20 here, and this is a problem in your book on page 53, and it is representing commuting times, so how long it takes people to get to work in, I guess, New York City. Um, so we're going to find the median, the mean and the median of this data. And first, we're going to calculate the mean. So what we would do is add each one, right? 10 plus 30 plus 5 plus 25 plus 40, so on and so forth, all the way to 45. And we add them all up, we sum them up, and then we divide it by our total number of observations, or our sample size, 20. And this is what it looks like. 10 plus 30, blah, blah, blah. We divide it by 20, and it's equal to 31.25 minutes. So what we would say is our average commuting time for workers or people that work in New York City is 31 minutes and 15 seconds, or 31.25 minutes. It's, that, you have to be that exact. You could leave it as this right here, but you want to make sure that you talk in context. And then the median. Let's arrange our data in a stem and leaf plot. Um, that way it's in chronological order. And let's talk about the shape real quick. This is skewed right. And we have a gap right here at 50. Actually, the gap is from 45 minutes to 60 minutes. So that's a gap of 15 minutes, which is a little weird. And so that makes us think that these values, they're probably okay, but they're definitely stretching out our distribution, making it a little bit more skewed. And especially this observation right here, 85 minutes is really dragging that skewness out. And that we will probably find to be, or we would say that that is a potential outlier. And we're going to actually learn how to calculate whether that's an outlier or not shortly. So make sure you label your graphs, so the key in context, and then you'll be good. So let's find the median. The median, this is a situation where we have an even sample size, so we will count 1, 2, well, sorry, so 20 plus 1 over 2, right? We already calculated this. It's going to be the 10.5 position, right? So we're looking for the 10.5 observation. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. So we're looking for the average between the 10th and 11th observation. That was 20 plus 25 divided by 2. And that comes out to be 22.5 minutes. So let's look at something right here. Our median is 22.5 minutes. Our mean is 31.25 minutes. Our mean is quite a bit higher than our median. So this is when we're going to get into talking about what is a better representation of center. And the answer is going to be the median, and that is because it is not affected by observations such as 85 or 60s and 65s, because it's based on position. It is the exact center of our data. It's based on position, so it is not affected by the lower values or the higher values that may be influencing this average, because it's affected, since it's involved in the sum right here. It's affected by every single observation. So that is why, because we have this high number 85 and these higher numbers 60 and 65, that's why this mean is dragged in the direction of those observations, and it comes out to be higher than the median. And that's why, especially with skewed distributions, you want to use the median, because it's going to be a better representation of the center of our data. because it does not it is not influenced by those outliers. I'm gonna run out of time, so I'm gonna switch over to our next video now. So